right, this is a quick little tutorial about a vector operation called the dot product. Dot products are going to be big if one vector has a component that is along another vector or helping it out. So you can see this vector A, if you take the shadow of it down onto B, it does have a component that's sort of helping B. Vector A also has a component that is perpendicular to B, but that does not assist in the dot product. So an easy entry into dot products is to just look at what the sign of a dot product would be. So in this upper left case, you can see this vector A does have a component that's along B, and so the dot product here would be positive, right? In this second case, which is in the upper right, the vector A is perpendicular to the vector B, and so it does not have a component that is along B, and so that dot product is going to be 0. In this bottom case, if you take the sort of the shadow of vector A that would be kind of along the direction of B, you see that it actually points in the opposite direction to vector B. So in that case, the dot product is going to be negative. Right? So just to practice with this for a second, here's a few examples. So in the upper left, what we're looking for here is if the dot product is positive, negative, or 0. Well, in the upper left, it's going to be positive because one vector does have a component that is along the other vector. If you look at this top right case, that dot product is going to be negative because this blue vector, if you take its shadow sort of along the yellow vector, you can see that it has a component that is against the yellow vector. And so that's going to be a negative dot product. In the bottom left here, those two vectors are perpendicular, and so that's not going to have any dot product at all. It's going to be 0 dot product. Let's look at this case here. See if you can figure out whether this dot product would be positive, negative, or 0. That's going to be a negative dot product because if you take, say, the component of the yellow vector that would, say, be along the direction of the blue vector, you can see it actually points in the opposite direction. It's not helping the blue vector. And finally, this last case, you can see the two vectors are nearly in the same direction. So the dot product here is going to be positive. The yellow vector, for instance, has a component that is very much along the blue vector. Now, where do these things show up, say, in physics? Let's look at a little case, specific case here. It says a donkey tries to drag a block up a ramp, but fails, and the block and the donkey slide down. Okay, so everybody's sliding down. And what we're supposed to do is find the sign of the work done by different forces. And it turns out on this block, there are going to be 4 different forces, okay? One force would be what's called the normal force. It's the force of the surface on the, that is perpendicular to the surface, that's acts on the block. Another force on the block would be the force of the donkey. You could call it the tension in the rope, but we'll call it the donkey force in this picture. So that would be kind of trying to pull the block up the ramp, but failing, as we'll see. Friction would point up the ramp. And again, that's because the block is sliding down in my scenario, okay? So the block is in the act of sliding down the ramp. And then, of course, the fourth force would be gravity, or the weight, which is mg. And so those red vectors are all the forces that are on the block. But as we mentioned in the prompt here, the donkey fails and the block is actually sliding down the ramp. And so what we're going to try to do is figure out whether the work done by these forces is positive, negative, or 0. So we just need the dot product of the red vectors, the force vectors, and the displacement, which is the yellow vector. So let's look at these one by one. We're just looking at if the work is positive, negative, or 0. So if we look at the normal force is perpendicular to the way that it's moving. So the normal force actually does not have any component along the direction that it's moving. And so that is going to have 0 dot product, the normal force. So the normal force does no work. It doesn't contribute joules or rob them away from the block as it slides down the ramp, right? Now let's look at the force that the donkey applies. Well, the donkey is trying to pull the block up the ramp, but the block actually goes down the ramp. So the donkey's force is against the direction of motion. That is a negative dot product, right? So the donkey is not contributing to joules of kinetic energy that the block would get as it slides down the ramp. So the donkey does negative work. See if you can figure this out for the friction force. Like the donkey's force, the friction's force is pointing up the ramp while the displacement's down the ramp. So the friction is also robbing joules of kinetic energy away as the thing slides down the ramp. The only force that's actually getting work done is gravity, and it's because gravity does have a component, at least, that's along the direction of motion. So it does positive work, and it's because it has a component, this little thing that I'm indicating in blue, that is actually along the direction of motion. And so the dot product of the force of gravity and the displacement is actually positive, right? So look at how you mechanically take dot products, right? Well, here's two vectors A and B, and you notice that vector B does have a component that is along vector A. And so this would have a positive dot product. All right, so one way to calculate A dot B is multiply the magnitude of A vector by this component of B that is along it, okay? Now, given the way we've drawn the picture, it's adjacent to this known angle, so you could also write this B parallel as B cosine theta. So a way to find a dot product is magnitude A, magnitude B, times the cosine of the angle in between. Likewise, as we saw before, instead of finding the component of B that's along A, you could find the component of A that's along B. Well, that is also going to be A times the cosine of the angle between times B. And so you notice in these two different pictures, to get a dot product of A and B, you take the magnitude of A, magnitude of B, and the cosine of the angle between. And that's whether you're looking at the aspect of A that's along B, or, as we saw before, at the aspect of B that's along A. It's still AB cosine theta. AB cosine theta. So to see how you'll mechanically take dot products in a specific example, here's two vectors. Here's one that has components go over 3, go up 3. And this one has components of going over 6 and up 0. And we're going to take the dot product of these two vectors actually in 3 different ways. So these are the 3 representations that we're going to look at here in this example. One representation is A parallel, the component of A parallel to B times B itself. So let's look at this one first. Well, A parallel, you can see this vector is going over 3, up 3. So this A parallel component is clearly just 3. So A parallel times B would be, well, A parallel, as we figured out already, is 3. B has length 6, so 3 times 6 is 18. So these vectors have a dot product of positive 18. Another way to get the dot product is AB cosine theta, or magnitude A, magnitude B times cosine theta. Well, magnitude of A is square root of 3 squared plus 3 squared, or square root of 9 plus 9, or square root of 18. So that's the magnitude of A. The magnitude of B is just 6. It's 6 units long. And the cosine of the angle between them, well, since this vector is over 3, up 3, that's got to be a 45-degree angle here. So you know the cosine of that thing is root 2 over 2. So if you take magnitude A, magnitude B times cosine of the angle between, well, 18 times 2 is 36. That would be root 36, which is 6. Times 6 makes 36. Divide by 2 makes 18. So you see we get the same answer that we got before. And then the final way of taking a dot product is probably one of the more popular ones. If you're able to do it this way, it's quite simple. Here's vector A and here's vector B. You get effectively the same thing by multiplying the x components together. So 3 times 6, store that number in the bank. Multiply the y components together, 3 times 0, store that number in the bank, and then simply add them together. 3 times 6 plus 3 times 0, or again, that would be 3 times 6, the x components, multiplied together, plus the y components multiplied together, 3 times 0. And that gives you the same answer of 18. So those are 3 different ways of actually doing the same thing, which is taking the dot product of 2 vectors.